Hello everyone, welcome back to alkaline hydroxide 784, and today in the chemistry series we will be doing the solubility equilibria. Okay, so far we've been looking at Kc, Kp, reaction kinetics, just normal chemical equilibria, then acid-base equilibria. So now the final one is solubility equilibria. So as the name suggests, it's about how much something dissolves in the solvent in a way. So so in solubility equilibria, instead of looking at a reaction or even acid-base dissociation, we look at how much something dissolves in a solvent. Usually it's water, so yeah, we'll just say water at 25 degrees Celsius because that's just how everything is defined in A level. um, yeah, so that's basically the idea here. And we know that there's something that dissolve completely, like salt, like common table salt, that's what I meant. But there are some other salts that do not dissolve completely, like the stuff you see in your chemistry practical. There's some that are only very slightly soluble, or they look like they do not dissolve, but there's a very small fraction of it dissolving. So that is where we have the KSP, or the solubility product, coming in. And in your equilibrium, we have the undissolved substance on the left, and then the ion that it will become if it gets dissolved on the right. So you will look at that with an example later on, I think. Or maybe let's just look at something that we can, like, we use the thing from the example and then talk about it in greater detail later. So the thing that we are gonna look at later on is the silver halide compounds. So like silver chloride, silver bromide, silver iodide. And silver chloride, obviously it doesn't dissolve very well. So what we do is, you can say that there is a very small dissolution of silver chloride, but most of it doesn't dissolve in water, like just plain water. So how we represent that is, we write silver chloride on one side, and then we draw the equilibrium arrow, and then on the other side we put the silver plus and chloride minus in aqueous form, in the sense aqueous state. And the KSP is then calculated as the product of the silver ion and the chloride ion over the silver chloride. Of course, like with anything else, we imagine that there's that water there, but we don't actually have to write the water in at this point of time, because we can just write aqueous on top of the arrows and we kind of have the same logic. So yeah, so the KSP is the product of the ions over the product of the initial like the salt or whatever that you're dissolving, like the concentration. I mean, it's not really a product, just one concentration. Yeah, you get what I write there. Okay, so that's pretty much how you calculate it. So if you get like the data in your question, and it clearly tells you how much is this ion, how much of that ion is there, you can kind of infer how much of the other ion is there as well. Or if if the solution already has a certain amount of ions, which we will talk about later, you have to take note of that, like put that into the equation as well. So to calculate KSP, just make sure you have the right value for each of the concentrations of the ions, because it's important to know that the ion may not necessarily come from the thing that they're dissolving, but also be present in the solution as well. Like for example, if you put AgCl and then you put something like KCl inside the water already, then there's definitely going to be way more Cl minus ions than Ag plus ions, and you had to write that number into your equation as well. And vice versa, if you want to find out how much has dissolved, you can do the same thing that we did with acid base and everything. We basically have that small s, and we assume that the dissolution is very small. So we can we have the KSP equals to Ag plus concentration of Ag plus and concentration of Cl minus, or AgCl, concentration of AgCl, and from there we represent the concentration on the top with S, so it becomes S squared, and below we have the initial minus S, and we can assume that S is so small that the bottom part can just become initial concentration, and then you can do the same thing as we did last time. Yeah, so if you do not understand what I'm saying, go and watch the previous video. Okay, so the next one is discussing the effects of the solubility by two different things. The first one is the common ion effect. So if you want to look at it from the equation, from the calculation standpoint, when you have more of one ion in the whole thing, right? Like you don't know what the KSP is, but you have the concentrations of all the ions. So let's say you have of course, AgCl isn't really the perfect example just because there is another complex that it does with the Cl minus ions. But we use a different salt for it then. Maybe like iron oxide or something. And then, okay, so imagine we have something like iron oxide or something like that. And then you write the equation for it, and imagine that you had way more iron plus ions to begin with. So what happens is, if you look at the equation standpoint, the top part will have like a larger value as compared to earlier for the iron plus ions, but the O2 plus may be a little bit lesser now. So you have to look at it in terms of the actual equilibrium. So when you have a lot of one of the ions on one side, it is more likely to become undissolved again. So the overall concentrations of both of them will end up decreasing, and the final product can affect the KSP in a way. The KSP is the same, but in the sense that both the top part and the bottom part will have the same proportional increase or decrease. Yeah. But if you want to look at the solubility itself, that S that we talk about, the S is now lesser just because there is too much of all the ions, and therefore it is prompted to go back to the undissolved state. So this is just like any other, like Le Chatelier's principle kind of thing. So let's say if you have iron oxide becoming iron 3 plus and O2 minus ions, and then you have too much of, you decide to add a bunch of iron 3 plus ions to the solution. Oh my, that's a tongue twister for itself. Anyways, if you do that, then there's too much of ions on one side, and like it's kind of messes up the equilibrium, and to restore the equilibrium it will try to undissolve some of the ions that are in the solution. Even though the solubility is already so low, it will become even lower, and the solubility will decrease even more, just because there's a lot of excess ions of one of the elements in the solution. Yeah. So the next one is, the second effect is the formation of complex ions. Of course, the thing I was mentioning earlier isn't the thing that we're going to talk about here, the AgCl forming a complex with the Cl minus. Of course, it can do that. So what happens is, even though you put extra Cl minus ions, what happens is that the Ag forms another complex ion with the chlorine, and it becomes AgCl2 minus or something. And then because of that, it actually becomes more soluble. The solubility increases because a lot of it has been used up into this other thing, like this other ion that is soluble. So now the free Ag plus ions and Cl minus ions have been decreased, and therefore the more of the AgCl can dissolve. Yeah, that's pretty much how it works, I think. But that's not the thing I'm going to talk about right now, which is, we're going to talk about a different thing, which is something that you actually do in practical. which is the reaction of Ag halide compounds with the ammonia basically. Of course, the first step is to actually add the silver into the halide ions. So you have your Cl minus, Br minus, or iodine minus in the solution. And to identify them, you just add some silver ions, silver nitrate, because silver nitrate is pretty dissoluble. It doesn't need to have a, it has a, I'm not sure if it's completely soluble, but it's almost completely soluble. So yeah, that dissolves pretty well. And then we have the silver interacting with the halide ions to form an insoluble product. The reason why it actually forms the insoluble product is because now in the solution there is too much of silver ions and chlorine ions, which kind of you know, how do I put it, which kind of makes the silver halide compound form. It's something to do with the concentrations of both being over the KSP or something. So as long as the concentration of the silver plus and the Cl minus, the product exceeds the KSP, silver chloride will form in the sense. Yeah. So that's a general way to find out how much you need before it becomes a solid. Yeah, so I was like, okay, so when that happens, you can then have that whole equilibrium set up. So I'm gonna just read out the three KSP values. So for AgCl, the KSP is 1.77 times 10 to the power of 10. For AgBr, it is 5.35 times 10 to the power of negative 13. Oh, sorry, the first one was what? First one was negative 10, 10 to the power of negative 10. Then second one is 10 to the power of negative 13. And the last one is 8.52 times 10 to the power of negative 17. So that's for AgI. So this is very important. So just try to remember the relative magnitudes, or maybe I'll just write it down. And then from there, you can then explain the whole practical observation that you get once you add aqueous ammonia into the solution. So when you add aqueous ammonia, the initial thing that happens is that the ammonia kind of reacts with the Ag plus, and it becomes a different complex, which is Ag NH32 plus. Yeah, kind of, because ammonia doesn't really have a charge, so it's just NH3. So the overall charge is a plus. So it's an ion, and it's soluble in water. And therefore the Ag plus concentration decreases, and therefore you can dissolve a bit more AgCl until the Cl minus becomes a bit too much or something, I don't know. But with AgCl with sufficient amounts of ammonia, you can dissolve all of the AgCl. It's possible, but when you do it for AgBr or AgI, it doesn't seem to dissolve it as much. So AgBr, there's a slight dissolution of the AgBr. For AgI, it's almost non-existent. And that's what you observe. And it's because of the relative magnitude of the KSP that I just told you. So for AgCl is 10 to the power of negative 10. So when the KSP when the equilibrium is shifted towards the left, the right, it actually dissolves all of the AgCl eventually. But for AgBr, it is a way smaller KSP. It's like 1,000 times lesser than AgCl, and therefore it's a little bit harder to dissolve it, and only a little bit of it dissolves. And for AgI, it's even worse. It's like 10 to the power of negative 17, so it's like 10 to the power of 7 times lesser than AgCl, so it will hardly dissolve. And that's why you actually observe that in your actual chemistry practical, AgCl dissolves when you add aqueous ammonia in excess. AgBr, it dissolves a bit, but not entirely. If you have a very keen eye, you can tell. AgI doesn't dissolve at all. So yeah, that's pretty much it. That's how it works. And yeah, there's nothing much to really say about solubility equilibria. You just need to take note of these two effects, the common ion effect and formation of complex ions. This can be applied to other examples as well. So if you're interested in more examples, I'm pretty sure there'll be some in the practical series, so you can go and check it out there. It's mostly useful for the practical application, and usually when they ask this, they may give you some data like a table or something, or they may say, oh, they are testing the quality of the water or something, that kind of context. So that's pretty much where you get the solubility equilibria going. And yeah, that's pretty much it. I mean, solubility equilibria can be, like, the equilibrium can be affected by things like adding acid or formation of complex ions, and for like adding one particular ion into the solution and things like that. So especially if there's multiple solubilities going on at the same time, there can be a lot of things going on. And yeah, just calculate things separately for each of them, and also take note that the presence of all of the ions in the solution, and also the temperature and stuff like that. Usually we are looking at 25 degrees Celsius in water as a solvent. So yeah, hopefully you'll be able to explain the things with this regarding this pretty well, so don't worry about it. Yeah, that's about it. I have nothing else to say. So yeah, if you found this episode useful, you can press the like button and subscribe. And with that, I would like to say thank you and bye.